Hey there, AP Chemistry students. We're now at section 2.4 on the structure of metals and alloys. Our learning objective for this one is to represent a metallic solid and/or alloy using a model to show essential characteristics of the structure and interactions present in the substance. So in section 2.1, I talked about how metals have their own type of bond, which we call metallic bonds. It's sort of similar to ionic substances in the sense that they form like a crystal lattice. They form like a grid that has a certain geometric arrangement. And with metals, it can be sort of like a cubic square grid or a hexagonal grid. There's a couple different varieties that it comes in. But the big difference between the crystals that metals form and the crystals that ionic solids form is that in metals, the electrons, the valence electrons, are delocalized, meaning the electrons aren't necessarily bound to the atom that they came from, or bound to any atom at all. As you can see in the picture here, we have a grid of positive metals that have been stripped of their valence electrons, and then those valence electrons kind of hover around in between, making what people usually refer to as a sea of electrons. And these electrons are able to like freely hop from cation to cation and move throughout the material, and that's what makes metals so conductive. So, lot of metals are usually a solid element, meaning one type of atom, but different metals can be combined to make what are called alloys. So an alloy is when you blend one or two or more types of metal together to make one single structure. And these alloys can come in two different forms. One is called a substitutional alloy, and in a substitutional alloy, you can see here as an example, we have a bunch of red atoms, and then we've replaced some of them with blue. So we've substituted some of the atoms for a different element. And you'll notice that even though the blue is somewhat smaller, it's at least big enough that it can fit into a place where the red would without changing the structure of the whole. So substitutional alloys are made when the atomic radii of the two metals are similar. There's also something called an interstitial alloy where the atomic radii are not similar. So we could see here in our example of an interstitial alloy, we have all of the red ones, but we've sort of shoved some little green ones in between. And you can see that the atomic size of the green ones are way too small to like fit in place of one of the red ones without sort of changing the geometric arrangement. So let's look at some examples of substitutional and interstitial alloys. So a really popular alloy that's substitutional is brass, which is mostly copper, but you've replaced about 30% of the atoms with zinc in the structure. And if you look at the atomic radii of copper and zinc, 140 picometers versus 139, they're almost identical in size. So the zinc is able to fit in there very nicely without changing the structure at all. But what it does do is change the physical properties. Copper on its own is usually pretty soft and it oxidizes pretty quickly. And zinc is a pretty sturdy metal that's kind of hard to make things out of. So by blending these two, this soft metal with this sort of sturdy metal, you end up with something that's more in between. So it's stronger than copper, and it's more ductile than copper, meaning you can like pull it and stretch it into wires and have it still hold its structure. And it's also done for aesthetic purposes because, as you can see in this picture here, the brass is a little bit more golden, and I think a lot of people like that for decorative purposes. But it also works good for decorative purposes as well because the brass does not tarnish as fast or oxidize as fast as the copper. You can also see this looks like a simulation or something, but you can imagine that they hit this copper on another surface and it dented, but with the brass it did not dent as much because it is a much stronger alloy. So a good example of an interstitial alloy is steel, which is actually not a combination of two metals. It's a combination of iron with a bit of carbon added to it, where the carbon ends up making about less than 1% of the total atoms in the structure. And you can see with the sizes of iron and carbon, carbon is a bit more than half the size of iron. So it's not going to fit nicely in the structure the way that copper was with zinc. But by adding this carbon in there, it actually makes the metal like less malleable and more heat resistant. And it also gives it more strength and makes it less brittle. Brittle meaning easy to crack. I'm sure if you've ever seen these like cast iron pots versus like a steel pot, the cast iron pots are good for like absorbing a lot of heat, but if you were to like drop it off the top of a roof, it might crack, whereas like a stainless steel one would probably just dent and roll away. Um, Anyways, that is all I have to say about metals and alloys, so I'll see you in section 2.5.